Section 1.4 continued, solving inequalities. With this continuation, we're going to start with compound inequalities. A compound inequality is a pair of inequalities joined by and or. To solve a compound inequality containing and, find all values of the variables that make both inequalities true. This is an intersection. So the word and refers to an intersection, what is shared by both quantities. And we'll see an example of that later on. To solve a compound inequality containing or, find all values of the variable that make at least one of the inequalities true. This is a union. So here we want to solve both inequalities, and here we want the shared and unshared part of the solutions that satisfy both sets of inequalities. Our first example wants us to solve each compound inequality and graph the solution. So here we have the term and, so I know I have an intersection. So our solutions for x have to be what's shared for both inequalities. So what we want to do is solve each inequality separately. So let's solve negative 2x less than or equal to 10. We need a positive 1 coefficient on the left, so let's divide by a negative 2. When I do that, I'm going to get x, and on the right, I'm going to get 10 divided by a negative 2 is a negative 5. Recall from the properties of inequalities that when I multiply or divide by a negative value, I'm going to then flip or reverse the symbol, so I'm going to end up with x is greater than or equal to a negative 5. On the right, I'm going to end up with 3x is less than 12, divide both sides by 3. That gives me x is less than or equal to 4. Now what we want to do is actually graph the solution on a number line. We're going to graph each one separately to see what that looks like and then find out where the intersection or the common points of the shading are going to be. The actual solution is x is greater than or equal to a negative 5 and x is less than 4, but we want to see that on a graph. So if I'm going to graph x is greater than or equal to a negative 5, here on the number line, I'm going to go off a little bit, would be a closed point, and then I would shade everything greater than a negative 5. On the other problem, what I would have is graphing everything less than 4. So I'm going to graph here that all points with an open point of at 4 and all points less than 4. If I would see where these are shared is this point is covered, so it's shared from this point on, which is a negative 5, and it's shared not here because the red line has a solid point at 4, but the green line does not have a solid point at 4. So the only shared parts are actually from a negative 5, which would be a solid point or a closed point, and at 4 would be an open point because they both don't share that. And then I would shade in between those points because that is the intersection of the x values or the x values that are shared between both quantities. So my true solution is the graphing with a closed point at negative 5, the open point at 4, and all shading in between. Also, after we graph the solution, we can write an intersection a little bit differently. Since these two share, we can actually write them as a shared solution with x in the middle. And then what we do is write this from small to large, and we make sure that the arrows are going the same direction. So we would start x is greater than or equal to a negative 5, and x is less than 4. This is acceptable. You may always see this type of notation, but this is also demanded when graphing. Our next example also is an intersection, and I know that because of the term and in between my two inequalities, so this is an intersection. So that means my solution on the number line, and when I solve it, need to be the shared values of x that make both inequality true. So let's solve each one separately. Divide by 5 on 5x is greater than or equal to 10. That gives me x is greater than or equal to 2. Divide by 2 on 2x is less than 14. That gives me x is less than 7. And since this is an intersection, we know that they're shared, so I can put x in between and then write 2 and 7. Of course, we read from the middle x term first. X is greater than or equal to 2. X is greater than or equal to 2. And x is less than 7. Now what we want to do is to graph the solution. So let's graph this one first. Since this is an equal sign with a greater than symbol, we're going to have a closed point at 2. I'll do this off the graph to show the representation of the intersection. And then I'm going to graph all solutions for x greater than 2. On the next one, I'm going to have x is less than 7. So at my location of 7, I'm going to put a open point and graph to the left all values of x less than 7. Now I need to identify what is shared. Here on the red line, that location on 2 is closed in, and on the blue one it's closed in, so I have a closed value at 2. At 7, I have a closed value on the blue, but not on the red, so that marks the location on 7 to be an open point. And all shared values for the solution are all values that are in between 2 and 7. Our next problem has the intersection combined. So when it is combined, we know that this is an and I know that it is an intersection. And my two inequalities need to be broken up. For example, I start with x. X is greater than or equal to a negative 8, and x is less than 1. Both of these inequalities are already solved for, so all I need to do is actually graph them. Here I have x is greater than or equal to a negative 8, so I'm going to show that off the line. Again, you don't need to do this once you get used to graphing it. This is just a representation of how to get to the real solution. So again, that's a closed point, and then I'm going to graph or shade any region where x has greater values than a negative 8. On my next inequality, what I'm going to have is x is less than 1. So at 1, I'll have an open point and shade all values that represent x less than 1. Then I want to combine these two for a solution on the number line. So here I have a closed point at negative 8, and it's closed on the green also, so that's a closed point. At 1, I have a closed point on the red, but on the green it's an open point, so it will remain open. And then I want to shade all values in between, because those are the values that are shared for the red and green graphs. And this is the solution to that compound inequality. Our next example, negative 8x is less than or equal to 16, or 3x is greater than or equal to 18. The or represents a union. Therefore, when I graph, I want values of x that make the left inequality true and the right inequality true, whether they actually are shared or not. So again, let's begin by solving each inequality. On the left, I'm going to divide by a negative 8. That gives me x. 16 divided by a negative 8 is a negative 2. And of course, by the properties of inequality, that tells me my inequality needs to flip or reverse. So that is going to give me x is greater than or equal to a negative 2. Here, divide by 3 on both sides. X is greater than or equal to 6. The solution is x is greater than or equal to a negative 2, or x is greater than or equal to 6. So let's take a look at this on a graph. If I graph x is greater than or equal to a negative 2, at 2, again, I'm going to represent this off the line to give a representation, and then we'll actually graph the solution. At negative 2, it's going to be a closed point because greater than or equal to. And I'm going to graph all values greater than or equal to that negative 2, so it goes to the right. On the next one, I have x greater than or equal to 6. So what I'm going to do is go to my location on the number line, which is 6, and I'll graph all values that are greater than or equal to 6. Again, that's a closed point, and that represents all values to the right also. So what is the total solution of this problem? Well, it's everything that unifies both the green and the red. So therefore, our true solution has to be, yes, it starts at 2 -2, and it's a closed point, and that represents all graphing to the right. I know that it is not shared between the 6 and the -2, but a union means it does everything. So my true solution of this is actually x is greater than or equal to a -2, because that encompasses x is greater than or equal to 6. So this is our true solution, which is written like that. Our next example has two inequalities with an and. Therefore, this is an intersection. Therefore, my solution is going to be all shared valued for x that make each inequality true. Let's begin by solving the inequality on the left. Here, I need to get the variable terms on the same side. I would subtract 3x on both sides, but that would leave me 0 on this side. Then I have to take the x back over. So the easiest thing to do is just to subtract 2x to start with. That leaves me a -1, less than or equal to, and then 3x minus 2x just leaves me x. So x, we always read by the variable first, x is greater than or equal to a -1. We're going to do the same thing on the other inequality. Here, if I subtracted x, I'd end up with a 0 and have to do more work. So the quickest thing is actually to just subtract 4x on both sides. And what that gives me is x minus 4x, which is going to give me a -3x, is greater than a -9. Divide by a -3. And that's going to give me x and 3. And recall from properties of inequality, when I multiply or divide by a negative value, that's going to flip or reverse my symbol. So this is going to be less than. And what I can do is, since this is a intersection, and I can combine these. So x is greater than or equal to a -1, and x is less than 3. And when I graph this, I'm going to graph off the line just as a representation, and then it will graph the solution set on the line. I'm going to have x is greater than or equal to a -1, so I have a closed point at a -1. X is greater than, so the values are to the right of that represent x greater than 1. I know that I have x is less than 3, so that's going to give me values. When I graph 3, it's going to have an open point because it's not equal to. And then all values less than 3 are to the left. Now I need to represent the intersection, or what shared values of the green and red line. On -1, they're both closed on the green and red, so it's closed for a -1. On the 3, it is closed in the red but open on the green, so they're not shared, but that represents where the location goes to. And then all values in between represent the intersection of these two inequalities. In our next example, the compound inequality is joined. Therefore, I know that this is an and it is an intersection. Therefore, the values for x must be shared between both inequalities when I break them up. So let's separate the inequalities. This is a -6 is less than 2x minus 4, and 2x minus 4 is less than 12. Then I solve each inequality separately. So I'm going to add 4 on both sides. That gives me a -2 is less than 2x. Divide by 2. X is going to be greater than a -1. Again, we read from the variable first. X is greater than a -1. Here, I add 4 on both sides. That gives me 2x is less than 16. Divide by 2. X is less than 8. And now we can join these together again and get a -1 and 8, and then x is in the middle. X is greater than a -1, but x is less than 8. Now, all I need to do is to graph the solution. X is greater than a -1. At a -1, I have an open point, and then I shade all values of x greater than that. On the next one, I have x is less than 8. Therefore, at 8, I have an open point, and shade all values to the left, which represent values less than 8. Now, all I want to do is to graph the solution of these two inequalities, and it's shared because it's an intersection. Therefore, at -1, this is open, and that's closed, so it's open because they don't share that. And at 8, this is closed, but the green is open, so they're not shared, so I leave that an open point. And then I shade all values in between those points. Our next example is a union because of the term or in our problem. So we want to graph a solution that is shared and unshared values for x for both inequalities. Let's begin by solving the left inequality by subtracting 9 on both sides. That gives me 3x is less than a -12. Divide by 3. X is less than a -4. Or subtract 1 on both sides. Gives me a -2x is less than 4. Divide by a -2. That gives me a +1 coefficient for x. And here, I'm going to get a -2. But recall from the properties of inequalities, when I divide or multiply by a negative value, my inequality has to flip. So x is going to be greater than a -2. Now, I can graph this solution. Let's start with x less than a -4. At a -4, that is an open point. And I shade values for x less than a -4. And for x greater than a -2, that's an open point again. And I shade values greater than a -2. Therefore, when I actually do the solution of this, these are both the solution because a union is all solutions for the x on both inequalities. They don't have to be shared. So here, open point at -4, and then shade to the left, and open point at -2, and shade to the right. That represents all values of x that are solutions for both inequalities, the shared and unshared values. A pipe is to be 17 meters long with a tolerance of plus or minus 0.15 meters. In other words, it can be 0.15 meters greater than 17 or 0.15 meters less than 17. How much should be trimmed from the pipe 18 meters long to allow to meet the requirements? Our general formula is x plus 17, the amount to be trimmed, which is what x is, and it can be 17 minus 0.15 or 17 plus 0.15. In other words, it can be less than 17 or greater than 17 by that tolerance. And we have a pipe that's 18 meters long. Then we just solve each inequality, and what we end up with is that x, the amount to be trimmed from the pipe, can be greater than or equal to 0.85 meters to stay within the tolerance, which would give us 17.15 meters long, or we could actually cut off 1.15 meters, and then my pipe would be 16.85 meters long. In other words, it would still stay within our tolerance.